For number 82, we're first asked to list the possible rational zeros. Remember, the possible rational zeros are all the factors of the constant over all the factors of the leading coefficient. The leading coefficient on this problem would be 1. So there's going to be all the factors of 10. So 1, 2, 5, and 10 over all the factors of 1, which would just be 1. So we don't really need to write that. And these could be positive or negative. So really, plus or minus 1, 2, 5, 10, those are my options. Now, to actually find the zeros, I have to start guessing and checking, essentially. I'm going to put numbers in, see if they make this equal 0. Or I can synthetically divide and see if I get a remainder of 0. Those are equivalent. I'm not going to just guess and check everything. I try one, and it turns out it works. And again, I can use synthetic division as my test. When I synthetically divide, it turns out I will get a remainder of 0, which tells me 1 is a solution, a 0 of this problem. Now, here's the issue. That took this from an x to the 4th polynomial to an x cubed, a cubic. I need to get it broken down to an x squared, or a quadratic, to be able to factor or solve it in a plethora of other ways. That means that I have to go back to my possibles and find another number that works. If you try -1, it does not work. 2 does not work. It turns out that -2 will work. And what I can do is I can take this smaller polynomial and synthetically divide again. This time I'm going to synthetically divide by -2. And I see that when I do that, I do get a remainder of 0 again. So the original problem was an x to the 4th polynomial. When I synthetically divided the first time, that took it down to an x cubed. When I synthetically divided again, it took it down to an x squared. So this polynomial is actually x squared plus 0x plus 5. That's what this actually turns into. I can easily find the remaining zeros of this by setting it equal to 0 and just solving for x. So if I subtract 5, x squared equals -5. When I square root both sides, I'm going to get plus or minus root 5 I. That's 2 answers. The third answer was the -2. And the fourth answer was the number 1. So there's all 4 answers. This was a quartic, degree 4. There should have been 4 answers, and I found them. Number 83 is going in reverse. We're creating the polynomial from the answers. This is also going to use the conjugate pairs theorem, which basically said if a complex number is a 0, then its conjugate is also. Think of 3i as being 0 plus 3i. The conjugate, 0 minus 3i, must also be a 0. So even though I only told you 2, I actually have 3 solutions. 2, 3i, and -3i. So for the 3i, if that is a solution, there must be a factor of x minus that number, x minus 3i. Oops. Since -3i is a solution, x minus -3i, which would be x plus 3i, must also be a factor. Since 2 is a solution, x minus 2 must be a factor. And then from here, I'm just going to multiply everything together. It would make a lot of sense to multiply these together first since they're conjugates. If I do that, I've got x squared plus 3i x minus 3i x. Now in the back, you got to be careful. That's going to be negative 9i squared. But I squared is negative 1, so that's going to be plus 9. So all of this stuff simplifies just x squared plus 9. I still have the x minus 2. Oops, not x plus. X minus 2. Oops, come on. There we go. And if I FOIL those together, I get to my final answer, which is going to be x cubed minus 2x squared plus 9x minus 18. For number 84, we're using Descartes' rule of signs to figure out the possible positive and negative real zeros of this. So the first thing I do is to deal with the positive possibilities, I look at the sign changes of g of x. So g of x, the first term is positive, positive x cubed. The second term is negative. The third term is positive, and the fourth term is negative. I count how many times the sign changes from one to the other. 1 change, 2 change, 3 changes. That means my possible number of positives is 3, or it always decreases by increments of 2, 1. Now, these aren't the actual numbers. These are how many positive real zeros. So this problem has either 3 or 1 positive real zeros. So it's at least got 1 for sure. To test for the negatives, I look at the sign changes in g of negative x. So if I were to replace every x with a negative x, that was a negative. This was a negative. That was a negative. Then I look at the sign changes there. Well, negative x cubed, that would be negative. Negative x squared, though, well, the negative would go away, so it doesn't change. The 5 already had a negative on it, so that would stay negative. 11 times negative x would switch that over to a negative sign. And then I've got my constant, which is negative. Notice there are no sign changes. It goes negative throughout, so there are no negative real zeros. It's not asking me to find them on that problem, it's just asking me to address how many there could be. For number 85, we want the end behavior, the y-intercept, the zeros, and then we'll do a graph. So end behavior, that is when I just focus on the leading term. It's odd degree with the x cubed, and it's positive. That means this is going to fall to the left and rise to the right. The y-intercept is actually very easy. If I plugged in 0 for x, every term would cancel out except for the 6 at the end. So the y-intercept is 0, 6. The zeros, the x-intercepts, that's what's going to take a while. I have to go back to my possibles, which is going to be all the factors of the constant, which was 6. So all the factors of 6, 1, 2, 3, and 6, over all the factors of the leading coefficient, which is 1 and 2. That's all the factors of 2. So my possibles, I actually have a lot here. I've got 1, 2, 3, 6, 1/2. 2 over 2 would be 1. 3 over 2. 6 over 2 would be 3. So any one of these positive or negative. I got to start guessing and checking by either plugging them in for x or synthetically dividing. I will tell you that -1 does work. So maybe you tried 1, it didn't work. You went to -1, it worked. Maybe you tried a different one and it worked, that's fine. But I know that -1 works. That means I can synthetically divide to crunch this polynomial down. And again, I'm hoping for a remainder of 0, which I get. So I just crunch this down to 2x squared minus 7x plus 6. That factors into 2x minus 3, x minus 2. Using the zero factor property, that leads to solutions of 3/2 and 2, which, if you notice, those were in my possibles. So I could have found them that way, but it just would have taken longer. So I now have 3 solutions to this problem. -1 is a solution, 3/2 is a solution, 2 is a solution. Those are the 3 places that it hits the x-axis. So do a little sketch of this graph. I know it hits the y-axis up at 6. I know I'm hitting the x-axis at -1. Let's see, 3/2, so 1.5, and 2. I know from my end behavior, I'm going to start down below, and each one of these solutions has a multiplicity of 1. They each only came up once. So that means it's going to cross through at each one of those. So I'm going to cross through, cross through, cross through. I started falling to the left, rising to the right, so we're good. For number 87, oh sorry, 86, this is basically asking the same question, except this time the polynomial has already been factored for me, so I don't have to go through all that. Now, for the end behavior, I have to imagine what this would look like if I multiplied it all out. Now, not all of it, because it don't actually do it, but I would have an x squared. The x minus 3 cubed would lead with an x cubed then. And then I'd have an x to the first. So altogether, the first term would be x to the 6th. I have 1, 2, 3, 4, 5. This is to the first power, so 6. So it'd be x to the 6th, and then some other stuff after that. But all I care about is the x to the 6th. That is positive and has an even power, so this is going to rise to the left and rise to the right. So my y-intercept, remember for the y-intercept, I'm plugging in 0 for x. I got to do a little more work on this. But if I plug in 0 for x, 0 squared times -3 squared times 1. Well, none of this matters since I'm multiplying by 0. My y-intercept is 0, 0. So it's going to hit at the origin. For the zeros, or x-intercepts, again, it's already been factored. So 0 is a 0, 3 is a 0, and -1 is a 0. So now I can set up my graph. I know this is going to hit at 0, 0, which also accounts for one of my x-intercepts. This is going to hit at -1. And it's going to hit at 3. Now, from my end behavior, I know this is going to start up and end up. Remember, when a 0 has even multiplicity, that means we're going to bounce off there. The -1 came from a factor that had odd multiplicity, so it's going to cross through there. So as I start this, I'm starting up high. I know I'm going to cross through the -1. 0 had an even multiplicity. That means I'm going to bounce off at 0. 3 had an odd multiplicity, which means I'm going to cross through at 3. And I ended up rising to the right, just as I thought I should. For number 87, we're using that intermediate value theorem. So this is a fancy way of saying plug in these numbers and see if their results have different signs. So I'm going to first plug in 1. So f of 1 so this would be basically 3 minus 4 minus 1, which is going to give me -2. So essentially what this is saying is when x is 1, y is -2. If I plug in 2, this is going to give me 3 times 16 minus 4 times 4 minus 1. If you run these numbers, you'll get positive, 31. So this means another point on this function is 2, 31. All this is saying for the intermediate value theorem is when x is 1, the y coordinate is negative. So there's a point 1, -2. But then when x is 2, the y coordinate is all the way up at 31. So the logic is, since a polynomial is a continuous function, it must be that there's at least one place in between those points where I cross the x-axis. There has to be at least 1, 0 between those. There actually could be more. It could have done something like this. A couple wiggles and gone up. I don't know. But there's at least one.